Hello all, I'm excited for today because today we dive into the world of Bayesian statistics. Bayesian statistics is an entirely new branch of stats, which allows us to marry our prior held beliefs and assumptions about the world with data that we've collected to have a statistically rigorous understanding of the concepts that we've already seen before. Bayesian statistics arrives from a completely new branch of philosophy, which in some cases allows us to have more intuitive and practical understandings of statistical concepts that we've seen in the past. For example, while we've dealt with confidence intervals, which arises from frequentist statistics, Bayesian statistics has credible intervals, which have a more intuitive interpretation. To show the power of Bayesian statistics, we're going to deal with the following scenario. We are going to be doing an analysis trying to find the true proportion of people that would say yes to a date with us. Now, since I'm a guy, I might slip up and start talking about the proportion of girls that will say yes to us, but of course this applies to girls and guys equally. The reason I chose this example is that we've seen in the past with frequentist analysis that we often have some minimum requirement of data that we need to collect before our results can be reliable. For example, we've seen this with the 30 data points that is said to be needed in order for the central limit theorem to quote-unquote kick in. But this may be a difficult threshold to hit in some scenarios. In this instance, it might not be easy to quickly find 30 people that you can ask on a date and record the results. After all, you may find quickly that if you get a yes from somebody and you tell them you weren't actually interested, you were just trying to collect data for a statistical analysis, soon the true proportion of people that will say yes to you on a date is 0. Bayesian statistics has the huge benefit of allowing us to put our intuitions into our statistical analysis itself. You may not remember exactly how many girls you've asked out or flirted with and how all those interactions have gone. But you probably have some gauge or proxy of what this true proportion of girls that would say yes to you would be. In order to insert these prior assumptions or beliefs, we use what in Bayesian statistics is called the prior. Our prior is a PDF that we define beforehand that gives us a sense of where we believe the true parameter of interest is most likely to be. In this case, we're talking about a true proportion, and so our range for our prior is from 0 to 1. Since for all functional purposes, we could think of this true proportion as a continuous random variable, we deal with probability density. In this sense, regions of our prior with higher probability density represent zones where we believe this true proportion of people who will say yes to us on a date is more likely to lie. In this case, this prior that we've defined says we believe it is likely that the true proportion of people that will say yes to us is between approximately 0.4 and 0.7. An important point to make is that our prior can technically be pretty much any function that we can mathematically define, meaning we have a lot of flexibility in what the prior looks like. That said, most priors will lead to a lot of mathematical computation for the analysis that we want to do, which is something that only very high-level programs can take care of. So in this case, we are using a beta distribution to define our prior, which has two parameters, alpha and beta. This beta distribution has the mathematical quality of making our computations a lot less difficult. We don't need to get into why this is the case, but it's important to know that though we're going to be using a beta distribution to define all our priors, this isn't strictly necessary for more complex analysis. Our two parameters, alpha and beta, allow us to change what our prior looks like. Prior with more spread means we have less certainty about what this true value is. For instance, here we have a symmetrical prior that concentrates around 0.5, but has quite a bit of variability around it. However, if we were to increase alpha, a more pointed prior like this means we feel more certain that this true proportion falls within a specific range, in this case, heavily concentrated around the 0.8 region. If we were feeling very optimistic, a prior like this would represent that belief. We have heavy concentration with a mean of 0.882 and a small standard deviation without much given variability, displaying that we are very confident this true proportion is within a small area. If we were feeling more pessimistic, thinking the true proportion of people that would say yes to us is quite low, we can change these variables to reflect that, giving us a prior that leans heavy on the left side of this range with an average of 0.122. Finally, we can even create a uniform distribution on this range, meaning we don't have any clue what this true proportion is. This prior, often called an uninformative prior, says that we have no input or sway on what we think this true proportion of people that will say yes to us is. For example, this prior would say that there's an equal chance that the true proportion of people that would say yes to us is between 0 and 5% and 95 and 100%. We can see just using this beta distribution, we have a lot of ways to express our preconceived beliefs about what this true proportion is. Let's change this a bit. to say that we think an accurate prior of this true proportion looks like this. There's still some room for it to be on the lower spectrum, but we're optimistic. Most of the probability density is concentrated above the 0.5 region. Now we have to go ahead and collect data. If we scroll down, we can see this process. Here we imagine that we run trials, asking people out, and record the number of successes, people who say yes to us. For instance, we can envision that we ask 5 people out, and 3 of them say yes. From here, we can define the immensely useful and somewhat magical posterior distribution. The posterior distribution tells us what our updated PDF of the true proportion should be, marrying together our initial beliefs via the prior and the data that we've collected in our trials. The posterior says if you really believed that this prior was an accurate representation of the PDF that best suits your guesses at what the true proportion of people who would say yes to you on a date is, then in light of the new data that you've collected, this is exactly how much you should shift your beliefs. That's an incredibly powerful thing to say because it allows us to take our initial assumptions and show us exactly how much we should be impacted or swayed by the data that we've collected. Further, we don't need to collect some 30 data points in order for this impact to be seen. The posterior distribution kicks in the moment we collect data. If we only had 1 trial and 1 success, we can see the posterior already kicks in. If we got 0 successes off our 1 trial, it shifts as well. The posterior is almost magic in the sense that the second we get new information, it tells us how to update our beliefs appropriately. Let's go through a couple important points of the posterior. First, as we collect more data via more trials, the posterior becomes more concentrated, regardless of the number of successes that we attain. This is very intuitive. As our sample size increases, as we've already seen, we become more certain about what this true proportion is. This is just the law of large numbers from a Bayesian perspective. We can see that by the time I've asked 19 girls out, we already have a much more concentrated posterior distribution as compared to our prior. We can see this displayed down here. Whereas the standard deviation of our prior distribution is 0.165, the standard deviation of our posterior is under half of that at 0.077. This isn't necessarily the case, that no matter what, if you add a new data point, your standard deviation will decrease, but is the case in the long run. As we collect more and more data, we single in on a smaller range of values that serve as plausible, true proportions. Another important feature of posteriors is that as we collect more data, the posterior distribution is less influenced by our prior. We can see this here. If we only run 2 trials and have 2 successes, let's say, our posterior is changed quite a bit by our prior. We can shift the prior to start to see how it affects the posterior. That said, look what happens as we collect more and more data. Running this up to 20 trials with 16 successes, we see that there's quite a bit less sway in the posterior as we change the prior. Yes, some, for sure, but we can have a prior that does not at all agree with the posterior, like this, and still the posterior stays relatively strong in its position. This is exactly what we'd want. As we collect more and more data, our initial thoughts or beliefs become less and less important. We can let the data speak for itself in some sense. But as we have a minimal amount of data, we care more about our initial beliefs. Now you have a sense for how we get our posterior and what it represents, but we still just have a PDF. So the real question becomes, what can we do with this new information? Well, Bayesian statistics can do essentially everything that we've seen in this course, just with slightly different philosophical interpretations and incorporating our own beliefs and intuitions via a prior. In this scenario, one real benefit of this posterior distribution is that we can define, for example, a 95% credible interval, which is essentially a confidence interval, but with that nice interpretation that we've been wanting the whole time. With a 95% credible interval, which we'll interact with later, you'll be able to say that there's a 95% probability that the true proportion falls within some range. Another big benefit of Bayesian statistics are what's called predictive distributions. Predictive distributions allow us to answer the questions that we care about in the first place when wanting to know what the true proportion is. When we've talked about true proportions, we've usually cared about knowing this value so we can run a binomial distribution. Remember that the binomial would tell us the probability of receiving X many successes given a sample size N and a true proportion P. In this instance, though we don't know P, our true proportion, our prior and posterior give us insight into the reasonable values that this P could take. Predictive distributions use fancy math to consider the entirety of the prior and posterior distribution to give us our best guess at what these individual probabilities are. In order to do this, we first need to set how many people we are theoretically asking out. Here it's set at 10. When we press on this, we can see these dots show up that represent the values in our predictive distribution. In order to get a better sense of the shape of these predictive distributions, I'm going to go ahead and change the axes real quick. Now we can get a good sense for what these distributions look like and how they vary from each other. All the orange points represent our best guess given our posterior distribution, whereas the blue points represent our best guess given the prior. For example, under the prior distribution, our best guess for the probability of 7 out of 10 girls saying yes to a date with us is only 0.010253, whereas under the posterior, this best guess now gets upgraded to 0.147152. That's quite an increase, meaning that the data we found was more optimistic than our initial prior beliefs. We can go ahead and see that as we change our prior, and thus our posterior as well, this impacts the results of our predictive distribution. Wherever we see more black lines between the two means that the posterior and the prior disagree with each other more. Like in this instance, where probabilities from the prior distribution seem to favor lower numbers of successes, whereas the posterior says that there's a good chance of 7, 8, or 9 girls even saying yes. We can see that our prior and posterior distributions heavily impact the results of our predictive distribution. Along with this, we can also go ahead and change the number of people we ask to find new probabilities. In this case, we've fixed that we're asking 10 people and want the probability of any number in that range saying yes. But we can, of course, increase this to get more points or decrease it for fewer. Finally, we could also change our data itself, which impacts only the posterior distribution. We see that as we shift this, the orange dots will begin to change because the orange points represent our posterior distribution, which is impacted by the prior and the data that we collect. Surely you can see by now the real benefit of this Bayesian method. We are able to take our prior assumptions and our data, no matter how limited, to get an updated sense of our best guess at the true proportion and the predicted distribution that would serve incredibly useful via this mathematical process. Let's go back real quick to looking at our prior and posterior as we do a recap. To conclude, Bayesian statistics is a branch of statistics that allows us to put in our preconceived beliefs via a prior, in this case defined using a beta distribution with our 2 parameters. In this case, we're making a PDF for where we believe the true proportion of people who would say yes to us on a date is more likely to lie. From here, we collect data via Bernoulli trials and record how many successes we receive. Combining this data with our prior, we receive a posterior, which is what our updated belief should be on this proportion. With these two in mind, we can create a predictive distribution if we set the number of people we ask, which transforms us from the world of probability density to probability, telling us the probability of any number of people X saying yes to us out of, in this case, 8. I know it may be a lot to process, but hopefully you can at least see the real benefit of this new method. We're going to go through another example of Bayesian statistics, so make sure that these fundamental ideas make sense in your head. Play around with this visual, changing the parameters to help build intuition. This may seem strange because it's a totally different approach to statistics from what we've worked with in the past, but there's reason to believe that this is the future of statistics, and Bayesian methods very well may become the standard in the industry, as our newfound computing power makes this method more achievable and leads to easier interpretations. You've made it this far, so I'm sure you can get through whatever else we throw at you. Thank you for watching, and as always, if you found this helpful, consider subscribing.